find each sum or difference by combining all like terms. When you're dealing with addition, in the past you might have heard, and so I'll get a little into the theory rather than just practice, but in the past you might have heard just drop parentheses and combine your terms. But the reason that's the case is because in each, or in front of each set of parentheses, there's an understood coefficient of 1, all right? Also known as a constant multiple or constant multiplier. That 1 gets distributed to each term inside the parentheses along with the corresponding sign, all right? So this one has a sign of a plus or a positive sign associated with it. This one, we assumed it was a positive one, so I could throw a +1 in front of that, or a plus in front of the 1, I should say. So this would distribute to 6 minus d to the 4th plus 9d plus d to the 4th. All right? So that's the justification for why you could just drop the parentheses when you're adding two expressions. All right? So we need to combine like terms. Now, again, a little bit with the theory here, but you can kind of cut corners along the way. So, do you need to show this step? Of course not. You know, you could just go to the part where you drop the parentheses. I just like you to understand why you're doing what you're doing. All right. Now, when it comes to combining like terms, what we're doing again is any term that has a coefficient. That's the easy stuff. Any term that does not have a visible coefficient has an assumed coefficient of 1. All right. So what we could do is tuck a little 1 in front of each one of these terms. All right. Now, what's really happening behind the scenes is this whole expression is getting reorganized to be put in descending order, which is to say the terms with the highest powers are coming first, then the terms with the next highest power are coming after that. Now this 6 has an understood operation of plus or positive. That would come off at the end. These like terms are being combined. So positive 1d to the 4th minus 1d to the 4th would become 0d to the 4th. Positive 9d minus 1d would become positive 8d plus 6. Again, another step that you wouldn't have to show. I would just like you to understand why you're doing what you're doing. All right. So this becomes 8d plus 6. All right. All right. So forewarning, just so you know, at the end of the unit, I'll be collecting these packets, and I'll be giving you credit for the notes that you take. All right. So, like I said, it's a traditional unit, but we actually haven't had a traditional unit in this course yet, so you wouldn't know what that looks like. So you don't have to complete the entire packet. You just have to complete what I complete in class. All right. Because the notes that you see here are going to be somewhat different than what you see on an answer key. All right, so when I write down something like this, like number 1, I'm going to be looking for that in particular when I check your notes. All right, I think that's only fair.
Does it have to be like written that certain way, or is it okay like if we solve it on our own and say that I got 6 plus 8d when I did this, would it be okay if it's like that, or does it have to be that way?
Well, you could have that, but you also have to have my solution down too.
Okay.
Could you also say that just negative d to the 4th power and positive d Could you just cross them both out because they cancel each other out?
When you're doing it on your own, yes.
Okay.
All right, just for the sake of having this up on the screen as long as possible, I'm going to jump down to number 3. So again, another instance where we have addition. So now we can start thinking about, okay, now we understand why we're able to just drop the parentheses, because if you compare what we started with here, let me just get a brighter highlighter. What we started with to what we ended up with, it amounted to the same thing. All right. Including the positive ones, distributing it and all that stuff didn't really amount to anything. But we had to do it the first time to understand that it wouldn't amount to anything, so that we would know we don't have to do that anymore. All right, so in number 3, I could just write it as negative x to the 4th plus 13x to the 5th plus 6x to the 3rd plus another 6x to the 3rd plus 5x to the 5th plus 7x to the 4th. All right, so essentially just dropping the parentheses. Then we also learned in the previous one that we don't really have to reorganize the expression in order to be able to simplify, as long as we simplified by the like terms. So what I would do here is I'd look for anything that has the highest power associated with it. So I'd look across my entire expression, identify the highest power, which is the power of 5, and then find another term, including its sign, also containing a power of 5. And then I'd combine those terms. So that's going to give me an 18x to the 5th. All right. So by now, hopefully you picked up on it. If not, I'll just say it explicitly. You combine only the coefficients, you leave the powers alone. All right. Next highest power is the power of 4. In front of that x to the 4th is an assumed negative 1. Negative 1 plus 7 is 6, but it's a positive 6. All right, so there should be a sign as a connector. Now you'll notice I didn't put a sign for the first term, but it was only because it was positive. I mean, I could have put a little plus sign there, but then I would end up disregarding it anyway. So you just kind of dismiss it. All right, but the last two like terms are power of 3. The two coefficients are 6, so plus 12 x to the 3rd. All right, and like I said, you could just ditch that sign in the front because it doesn't really factor into the solution. Now, number 5 has a negative sign, so we'll kind of go back to the process we used for number 1, which is to say we're going to do a little distributing. All right, it's a good skill to have because I'll tell you, and this isn't just from my experience, I think this is, I saw it somewhere. I should research it. I should actually collect data and verify this, but I can say that the number 1 mistake in all of mathematics is sign distribution, aka somebody forgetting to distribute a negative. So this is where that skill begins. So let's get it right, and you'll avoid the number 1 mistake in all of mathematics. All right, so we have an understood positive 1 in front of the first set of parentheses minus, there's really an understood positive 1 in front of the second set of parentheses, but minus a positive becomes a minus. So I'm going to distribute through a negative 1, positive 1, and then a negative 1. So I'm looking at a positive 3, a negative 6n to the 5th, a negative 8n to the 4th, a positive 6n to the 4th, a positive 3n, a positive 8n to the 5th.
Wait, why is the second one? Oh, no.
All right, so we go through, we look for terms with the highest power, in this case power of 5, combine our like terms. All right, we got a negative 6 and a positive 8, so it's going to give me a positive 2. The next highest power is a power of 4. Negative 8 plus 6 is negative 2, so negative 2n to the 4th. The remaining terms are not like, as in they're not like each other. One has an n attached to it, the other doesn't, so they can't be combined. So I would put the plus 3, and plus 3n, and then the plus 3. All right. So just a word on that real quick. Again, a little bit about the theory. That 3 can be thought of as 3n to the 0th power. That 3n could be thought of as 3n to the 1st power. All right. Any number could be thought of as a number multiplied by a variable to the 0th power. All right. So that affects its placement within the expression, the simplified expression. All right. So we want to go from highest, when we say descending order, highest power down to lowest power, right, in order. All right, one more of those. Just cutting out a little bit of the fluff here. Since there was no negative sign in front of the first set of parentheses, we just dropped those parentheses. That's not an N. In front of the second set of parentheses, we do have a negative. So that's an assumed negative 1. That gets distributed. So negative 3m squared minus 11m to the 4th plus 7. All right, so by now you should be realizing that when you have a negative in front of parentheses, all you're doing is reversing the sign inside the parentheses. Some of the questions that you were asked to do in the assignment yesterday asked you to find the opposite of an expression. All right, finding the opposite is the same as multiplying by negative 1. All right, so making that recognition kind of helps streamline the process. So I'm looking for something that's like negative 3m to the 4th. That would be negative 11m to the 4th. Combine them, negative 14m to the 4th. The next highest power is a power of 2. So I'm looking for something like 10n squared. That would be negative 3. Oh, I wrote n again. I can't stop myself. 10m squared. So that would be negative 3m squared, which would combine 10 minus 3 is 7. So 7m to the second power. And the remaining terms aren't like anything else, and they're not like each other. That 8m in the front can be thought of as a positive 8m. So I would say plus 8m plus 7. All right. Now, you can check your work on Desmos. It's just kind of a pain because honestly, it's really just a matter of typing in your original expression and typing in your new expression and seeing if they match up graphically. It's a lot of typing. All right. So it's not the worst thing you can do, but I mean it is a time consumer. Right. So it'll be kind of tedious, but I want to get through the theory of why these things work the way they do in the hopes that it'll help you avoid making mistakes in the future. Because I mentioned this with the other class, but it's true. Like I tend not to make I tend not to make mistakes. Yeah, that's funny. I tend not to make statements like this without backing it up. But this topic is related to a lot of the things that you'll be covering in the future. But it's it's the number one cause of any kind of error that occur in algebraic solutions to more complicated problems, right? So yeah, we want to get this down, right? Because you'll find in the future, you'll either believe me or not, but in the future you'll see that almost every point deduction, like minor point deduction that you get on a math problem, comes from a concept related to this idea, right? So we don't want to gloss over this. So combining like terms is pretty conceptually straightforward. It's the idea that if you have two monomials, so two single-termed expressions containing the same variables raised to the same powers, then you can combine their coefficients, right? But when you're taking two polynomials, so each one of these is a polynomial, right? So this is a polynomial, and so is this. Oh, hand-eye coordination's a little off today. You're combining these two polynomials with parentheses around it. It gets a little distorted in terms of what you need to do, right? So in front of every polynomial, there's an assumed coefficient of 1, right? So I got a 1 here, and I got a 1 here. Specifically, those ones are positive. So this one's already accounted for as a positive, so I'm just going to tuck in a little positive sign here. Oh, and before we get too far ahead of ourselves, I should point out that since this is going to be a traditional unit, right? Traditional unit, like pencil, paper, note-taking, quiz, test, no project in this unit. What I've done in the past in situations like this is I collect the packets at the end of the unit. All right. And so what I look for in particular are the notes that we took in class. All right. So I don't compare it to the answer key because the answer key I actually haven't even posted the answer key yet, but I don't compare it to the answer key because people just copy that off the internet. What I do is I compare it to my class notebook here just to make sure everything is the way it should be in your pencil paper packets. That's alliterative. So yeah, make sure you get the notes down. That's a long way of saying copy down the notes. Very important. So I'm going to distribute the positive 1 here, and I'm going to distribute the positive 1 here. All right. And that's going to give me a negative 4k to the 4th plus 14 plus 3k squared. All right. And you'll notice that that's exactly the same as what you started with inside the parentheses. Because when you multiply something by 1, it shouldn't change the outcome. All right. Same thing with the other expression. So in the past, you might have learned that when you have polynomials or any kind of expressions and you're adding them together and there's parentheses involved, you just drop the parentheses and combine the like terms. This is the reason why that's the case, right? Because multiplying by 1 does not change the outcome. All right. So now what I'm going to do, again, I'm taking the long way around here, but again, it's for a purpose. we're going to use the commutative property to reorganize this so that it's in descending order. So I'm going to copy paste a little bit. Let me get rid of those highlights. All right, so what I'm going to do is take any term that has the highest power associated with it. Highest power is the power of 4. I'm going to group those together. Then I'm going to work my way down the line, say, okay, well, what's the next highest power? Next highest power is power of 3. I'm sorry, power of 2. So I'm going to take the terms that have powers of 2 associated with it. Now, the last two terms, it really doesn't matter that they're power of 0, but because they are like terms, they're just constants. But I did want to take a moment to explain that. The idea is that if you have a numerical value, just a constant numerical value making up a polynomial or part of a polynomial, there's an assumed variable raised to the 0th power attached to it. So it kind of gives you a sense of where the two values go in the pecking order. You wouldn't have to write the k to the 0th power. I just wanted you to at least have one instance where it's in your notes so you're aware that that's what the relationship is. All right. So we're not really going to do much with Desmos in this unit, but I figured I'll show you this one instance. Let's say I type in 14, just the number 14. 14 is 14. But if I type in 14x to the 0th power, all right, I'm going to look at the graph. I'll type them both in as y equals 14 so that it actually shows up as horizontal lines. You'll see that they both map to the same location. All right, because they have the same value. All right, that's the idea there. All right. So now that the expression's reorganized, I can group, well, I have grouped, I can combine like terms. All right. Combining like terms means leave the variable alone, combine only the coefficients. So I have negative 4 minus 3. That's going to give me a negative 7. Bring the k to the 4th along for the ride. I have a positive 3 minus 14. That's a negative 11. Bring the k squared along for the ride. A positive 14 minus 8 is a positive 6. Sign comes along for the ride as well as the k to the 0th, but k to the 0th is equal to 1, so it's dismissed anyway. All right.
I got the long one
All right. The next one, same deal, except we're not going to take the long way around here. All right, we'll just kind of streamline it. So we learned from the previous one that we could just drop the parentheses. So this becomes 9r to the 3rd plus 5r squared plus 11r plus negative 2r to the 3rd plus 9r minus 8r squared. All right. I reorganized the expression in the last problem so that the highest powers came first, and then the next highest powers, and then the next highest powers, and so on. But instead of doing that, what I could do is just take note of what the terms are with the highest powers and put the results in the appropriate order. So if you go by powers, so highest power, evaluate those expressions first. So combine those like terms, you take those answers and just put it down in the next line, but in the order of the highest power to the lowest power, then you'll have what you need. So for example, in this case, 9r to the 3rd minus 2r to the 3rd would be 7r to the 3rd. I started with the power of 3 because that's the highest power. All right. The next highest power is a power of 2, so I would take note of any term that has a power of 2. All right. So 5r squared minus 8r squared would be negative 3r squared. The only terms that are left have an understood power of 1. If you just see a variable without a power indicated, they're like terms, but they're also known to have powers of 1. Right? As opposed to just a constant which has power of 0. So 11 r to the first plus 9 r to the first would be 20 r to the first, or just 20 r. Now these three terms, these three remaining terms, do not have common powers. They have the same variable, but not raised to the same power. So they're not like terms, and then so therefore they can't be combined. All right, so much quicker. All right, we cut out a lot of the fluff. But now with number 6, I'm going to add all that fluff back in because we're dealing with a negative. All right, but we can streamline a little bit, but not too much. All right. So in front of the first set of parentheses, we have an understood coefficient of positive 1. But in front of the second set of parentheses, yeah, there's a 1, but there's also a negative sign already there. So that makes it a negative 1. So we're going to distribute the positive 1, which we learned in the last two examples doesn't affect anything. So all I'm going to do is rewrite the expression without the parentheses, at least for the first polynomial. For the second one, though, I'm going to distribute that negative. In distributing the negative, we're multiplying each term by a negative 1. When you multiply by a negative 1, you reverse the sign. All right? So negative 1 times positive 10 becomes negative 10. So negative 10a. Negative 10a. Negative 1 times negative 2a to the 5th would become positive 2a to the 5th. Negative 1 times negative 14a to the 4th would become positive 14a to the 4th. All right. Instead of like the first example we did, I copied and reorganized everything. We'll do what I did in the second example, and that is just take note of the terms with the highest power and combine them, and then work our way down the line. All right? Because after you distribute the negative 1, it now follows the same approach of addition, or as addition. All right? So 12a to the 5th plus 2a to the 5th would be 14a to the 5th. That's a positive 14. Right? I could put a positive in front of it, because you should really always consider that every term has a sign associated with it. It's just, when a number's positive, we don't write the sign typically, right? But if it's a term that's further down the line, like for example, in the next case, 14a to the 4th is getting combined with a negative 10a to the 3rd. So negative 10 plus 14, that's a positive 4. I absolutely need the positive here because it's connecting that to the 14a to the 5th. So this would be 4a to the 4th. Another little bit of theory, and I might be overdoing it, but it's really kind of strange when you think about it. But you got to start somewhere. Every number system starts somewhere. All right, whether it's negative infinity or 0 or positive, whatever. So polynomials all start at, and there's more to this, so I'll write it in a second. But polynomials all start with a numerical value. That numerical value is, oh, sorry, that's the power of 3, right? Okay, so they don't combine. I'll get that in a sec. I saw the confused looks, so I knew I made a mistake somewhere. I'll get to that in a sec. But polynomials all start somewhere, and that somewhere is 0. So in every one of these cases, there's an assumed 0 as your benchmark. So it's 0, then what? All right, 0 minus 7k to the 4th minus 11k to the 2nd plus 6. Then 0, well, what's the connector here? It's not multiplication. It would have to be a plus. 0 plus 7 to r to the 3rd minus 3r squared and so on, right? In this case, it's 14, but 0 plus 14, a to the fifth, and so on. All right, so those connectors are implied because we don't actually write the 0, but they are important. All right, so we just got to keep that in mind. Because really, you think about it graphically, like where would this start on a graph? If this were y equals f of x, so some function of x, and all of these instead of a's, they were x's. Like when I graph a y value, like if I'm plotting a y value, where do I start? I start on the x-axis where y is equal to 0, and then I either go up or I go down. Going up is adding, going down is subtracting. All right? So these expressions give me the quote-unquote y value that I'm traveling from 0. All right? So yeah, we don't write the plus in front of the 14a to the fifth. We don't write the plus in front of the 7r to the third, but they're implied, and we should always keep that in mind. All right? Yeah, but as you probably correctly identified, the next term should be 14a to the fourth. And that's because there's nothing like the a to the fourth. There's nothing like a to the fourth. All right. Yeah, there are other terms that have the same variable, but not the same variable while also having the same power. All right. There's nothing like a to the third, so negative 10, a to the third can't be combined with anything. But then the negative 6a to the first can be combined with the negative 10a to the first, which will give you negative 16a to the first. All right. But again, you could write the power of 1 or not. It doesn't make a difference. All right. So what did we do here? Well, we had a negative in front of an expression. When we had a negative in front of the expression, we took the exact opposite of that expression and added it to the other expression. All right, so my first expression here was positive. All right, we just rewrite that without the parentheses. But for the second one, we're just going to reverse every sign in this set of parentheses. So it becomes positive 2y to the second, positive 3y, positive 9. Because that's what happened here. I had a positive 10, a negative 2, and a negative 14. It became a negative 10, positive 2, positive 14. Just reversing the signs. All right. So if you understand the effect to the cause, then this becomes very easy. And it actually becomes difficult to make a mistake because you're understanding the theory and not just following steps. All right. But now I have like terms. This is really a positive 5y to the second, but I'm just going to write 5y to the second. This is, well, two like terms, both having a power of 1. So negative 4 plus 3 is negative 1. So negative 1y to the first, or just negative y if you want. And then the last two terms are constant. You just tack those onto one another. So plus 15. Like I said, you could ditch the 1 here. You know, just like we introduce a 1 when it's just a negative sign, we can remove a 1 if they have it there in front of a coefficient. All right, so it's up to you whether you leave it in or take it out. I'll leave it in. Do it if you want, but I would rather just double check my work. All right. So then on page 6, all right, so those are all the different concepts from yesterday. You have a problem here. Ben was asked to subtract 7a squared minus 5ab plus b squared from 12a squared plus 3ab plus 4b squared. Shows his work. He made a mistake somewhere. We want to figure out where he made the mistake. And then solve the problem correctly. All right. So, well, let's solve the problem correctly first. and then go from there. All right, so we're subtracting from 12a squared plus 3ab plus 4b squared, which means that expression comes first. And from that, we're subtracting the 7a squared minus 5ab plus b squared. All right, so it's essentially the same type of problem we did on the previous page. The issue here is now we have a term that has two variables in it. All right? But if it has the same ingredients, same variables raised to the same powers, then they're like terms and you approach it the same way. All right? So I have an understood coefficient of -1 here. So I'm going to run through the -1. The first set of parentheses, I could just drop them. And we now know that multiplying by -1 is really just the same as taking the reverse or the opposite of whatever the expression that it precedes. Okay, so if I have a negative in front of an expression, all I'm doing is just taking all the signs of that expression and flipping them, making the positives negatives and the negatives positives. Okay. So my like terms, I have an understood positive 12a squared minus 7a squared is 5a squared. All right. Positive 3ab, positive 5ab would be positive 8ab. Again, same variables, same powers, that makes them like terms. All right, so it's got the same ingredients. In front of that b squared, we have the 4b squared. All right, so that's like the negative b squared, but in front of that b squared, we have an understood coefficient of 1. Right, making it a -1, right, because the negative's already there. So 4b squared minus 1b squared would be 3b squared, but positive 3b squared. All right, the sign always goes along with it. So I'd look at this, if I'm a student, I'd say, well, what about the 5? You didn't put the sign there. Well, I could have, but it would just go away anyway, right? You learned a long time ago that it's only the negatives that you have to sign. The positives, if I say the number 2, it's assumed to be a positive 2. It's only if it's negative that I got to put the negative in front of it. All right. So we have a solution. Now we got to look at what on earth happened in Ben's solution. Step 1 looked okay. Step 2 looks fine. Step 3, I have no idea what happened there. All right, so it looks like step 3. All right. So number 2 here seems like it's kind of a straightforward problem that doesn't really amount to much, but this is actually the kind of thinking that we need to have. All right. So the always, sometimes, never. This will work its way onto an assessment, so we got to be careful about this. The terms of polynomials are blank monomials. All right. So if you think about really everything we just did, each one of these expressions makes up a polynomial. All right. A polynomial is the multitude. The monomial is the singular. All right. So the ingredients that make up a polynomial is a monomial. All right. So the terms of polynomials are always monomials. the difference of two trinomials is actually sometimes a trinomial. All right, so what's a trinomial? The tri part of it, 3. So it's a 3-termed polynomial. All right, and the reason I say sometimes, I'll give you a quick example. Let's say, and this is the counter example that keeps it from being always. All right, so let's say I have x squared plus 2x plus 1. All right, and again, it's the difference. The difference implies subtraction. If I subtract from that x squared plus 2x plus 1, you don't really need to do any advanced algebra there to realize that you're subtracting two identical quantities. That'd be the same idea as if I took 5 and subtracted from it 5. The result is going to be 0. Right? That's not a 3-termed expression. Right? It's just a constant. Bottom line is it's not a 3-termed expression. Now, if I added them together, even though they said difference, but if I added them together, I'd get another trinomial. If I subtracted a different trinomial, I'd get a different trinomial, right? Not necessarily 0. But there are instances in which I would subtract trinomials and not get a trinomial. All right. All right. So a binomial is blank a polynomial of degree 2. Degree is the highest power, right? So it's the highest power contained within a binomial, right? Binomial is the number of terms. So this is the 2-termed binomial. Binomial, that's funny. So 2-termed polynomial. The degree of 2 is the highest power. All right. So some examples may be x squared plus 4, x to the 5th minus 2. Well, those are two good enough examples because they both have 2 terms. One of them has the highest power of 2, the other doesn't. So this is another sometimes. The sum of two binomials is blank a binomial. That's also a sometimes. For example, along the lines of the second one, if I have x squared plus 4 and I add to that a negative x squared minus 4, the result would not be a binomial. All right. But if I took x squared plus 4 and added to that x squared plus 4, I'd get 2x squared plus 8. All right. So I could get a binomial, but I don't have to get a binomial. All right. So in the next one where it says the sum of two binomials is blank a monomial, well, it's not always going to be a monomial either. So sometimes it could be a monomial, but sometimes it's going to be a binomial. All right. So they're both sometimes. The sum of two polynomials is blank a polynomial. Well, I think we've shown enough times that if you add two polynomials together, you could get a result of 0, which is not a polynomial, it's just constant. So this is also a sometimes. All right. So on the next page, you have the puzzly kind of thing, and that's going to be your homework. All right, so that's page 7. I'll put that in Schoology, but it's really just simplifying, coming up with the word that corresponds with the simplified expression, then putting that simplified expression, the word associated with that simplified expression down with the question number, and the little blanks at the bottom are the question numbers. Just put the words there, and you can come up with a fun response to the little prompt there. Use the code to discover an interesting fact.
We'll also finish the other half of that page we did.
No, that's all right. I'm gonna do that with the other class, and I'll post that up on YouTube. All right. So the rest of the time, whatever's left is yours to work on this.